So you probably saw that I put up the grades on Moodle now. I forgot to put them up actually. So now they're up with the grading sheets that are on there. I hope you can see that. Yeah. Okay. So the test rewrites, if you choose to do them, will be due 1 week from today, by midnight today. So you'll have also a quiz due that day, but right, you'll have like one problem for a quiz or something due that day. But remember that. Well, I don't think you don't need to include the original file because I have the original files, right? So just include the test corrections. Make sure it's clear what you're correcting. Okay, if you choose to do that. Okay. All right, cool. But everybody did pretty well, actually, which is good. It was a pretty narrow test, though, right? We weren't testing a whole lot of material.
Can
What
was
I?
the average?
Oh, I didn't calculate the average. Just 5 of you. It's kind of meaningless. Um, I don't know.
Can I talk to you for a minute after class?
Sure.
Nice.
Um,
Thank you.
yeah. So yeah, it was much better than usually. But like I said, it was kind of a narrow test where we're really sort of testing just the stuff in chapter 3, right? So not a whole lot of other stuff. All right. Okay. All right, let's get started. So let me share my screen. All right, so this is where we left off, right? So just to remind you, let me get my board, which I always forget to do before I log into class. It's weird, but all right. Wait a second. Okay. All right, so just to point out here where we were, right? So we were looking at the angular momentum L, and we found out again that we can only have simultaneous eigenfunctions of these 3 things here, right? The Hamiltonian L squared, right? The square of the length, right? That's Lx squared plus Ly squared plus Lz squared, and then the value of Lz. So these 3, and of course, like I said before, you could also choose L squared and Lx or L squared and Ly if you like, but it's kind of tradition to use L squared and Lz, all right? These are the eigenvalue, vector or function equations for each one of those operators, right? So we have h hat on psi, we get the energy back, L hat squared. On psi, we get this eigenvalue, h bar squared L plus 1, where L is our quantum number that associated with, well, at least in the hydrogen atom, right, associated with the angular momentum. And then Lz on psi, you get h bar times m, and m is the azimuthal quantum number. And just to recall that even though we're writing psi here, right, we really mean, like, for instance, for the hydrogen atom, sorry, your pictures, I can't seem to move them so that they are not in the way, but that is just bizarre. Why can't I do that? Give me a second. Okay, there we go. All right, so just like before we said, for the hydrogen atom, there is some R that depends on both the N, which determines the energy, and L, which is the angular momentum quantum number. But the eigenfunctions of these 2 things are the YLMs, the spherical harmonics, right? And recall that that is going to be true no matter what the system is, as long as we're in spherical coordinates, right? If we're solving the TISE in spherical coordinates, we're going to get the YLMs. We don't even care what the potential, well, I have to be a little bit careful, so there's a caveat. So in spherical coordinates with the potential energy function only depending on R, right? So that then you will get the YLMs for your equation. Their separable equations will be the YLMs. So this is on the condition. So In other words, this guy will be your angular solution to TISE if V of R theta phi equals just V of R, right? Okay, so you will get the spherical harmonics as long as this is the case. Okay, so you will have these eigenvalues, etc., as long as this is the case, no matter what the system is. Again, as long as this is the case. So, okay. Okay, so now we're going to move on to, and again, I said I was going to not prove that these are the eigen values and eigenfunctions, but you did have, I think, a problem on this. I can't remember whether it was a quiz or I can't remember now, but it was a quiz or homework problem where you're looking at what the operator for LZ looks like, right? Okay. And L squared also has a differential operator, and I'm just going to write those down. So in other words, remember how P, the momentum has an is as an operator is a differential operator, right? So for instance, Px is h bar over I partial x, right? Differential operator. Well, these also have L squared and LZ also have differential operator forms, okay? So L squared has the form minus h bar squared 1 over sine theta partial theta of sine theta partial theta, and then plus 1 over sine squared theta partial squared phi, right? This is the differential form of L squared, okay? Oops, this is, sorry, I didn't use my notation that I want. I should have, I was trying to use the full notation and then I forgot. Hold on. This would be partial squared partial phi squared, right? Okay. So L squared, if you acted this particular differential operator on the YLM here, right, you would get back this particular eigenvalue and the YLM, okay? And I wonder if this looks familiar to you. Can someone tell me if this thing looks familiar?
It looks like the funky thing we was working with when we were solving for the angular part of phi.
This is the angular part of del squared with an h bar squared in front of it. Right? Remember del squared? Right? In spherical coordinates? Big nasty thing. This is the big nasty part of it that's the angular part. Right? With a minus h bar squared out in front. Okay? All right. And LZ has a differential form, which is really, should be very reminiscent of your, P. It's h bar over I dd phi. Okay. So if you look at your angular, your spherical harmonics, if you go into the book, I have to go look and see where that is. Where are you, spherical harmonics? Is it Bessel functions? No, I don't want you. Here we go. So if you look at the spherical harmonics, for instance, anytime m is not 0, right, the azimuthal quantum number, the dependence is something like e to the, you know, plus or minus, or e to the im phi, right? So notice that if you act this operator on this function here, what do you get, right? You're going to get im, the i's are going to cancel, and you're going to get h, so your eigenvalue is going to be hm, right? So in other words, if I act this guy, so LZ acting on this, which is the only part of the spherical harmonics that has a phi in it, right? So these guys, the spherical harmonics, y, l, m of theta phi, all have the phi dependence of e to the im phi, right? No other phi dependence. Everything else is theta. Whatever complicated bits that are in the spherical harmonics, other than this, depend on theta. Okay, so this is a phi, sorry. Okay, so we act on this, right? It's h bar over I. I'm just going to do it out for you. And then partial phi, e to the im phi. And of course, that's im. So h bar times im over I, e to the im phi, right? And the i's cancel, and you just get h bar m e to the im phi, right? So the part of the spherical harmonic that has the thetas in it is just going to be ignored by this guy here, right? And of course, you can go through the machinations if you like to do all this and see what happens. But okay, all right. So so just to point out that they do have differential forms. These operators, okay, they do have differential forms. The differential form for L squared is not really used that often. Yes, you can probably see why. A lot of the algebra that you end up doing with L squared, you don't need to use the differential form. All right. All right. So now we're going to move on in chapter 4 to something that is super, super, super important. Not that all of chapter 4 isn't important, especially this being able to solve for the hydrogen atom. But what's really, really important to pretty much everything that we know and love, all the chemistry that makes our world possible, is something called electron spin. And all particles actually have spin. We're really going to concentrate on electrons, but we'll be talking about spin in general. And so that's what we're going to start with now. I'm going to get a new layer. Are we good? New layer, okay.
Have you been keeping up with the G-2 muon experiment? With
Yeah, it's really cool.
I think it's cool too.
Yeah, I'm very excited about it.
Yeah.
Yeah. Okay, great. All right. So first we're going to talk about an experiment. And it's called the Stern-Gerlach experiment. And you may have heard about that maybe in what, I don't know, advanced lab? You guys do anything like that in advanced lab? No? Okay. Sometimes, there's like Stern-Gerlach, apparati that you can buy. Apparatuses, whatever the plural is of that. And, you can actually have students able to do the Stern-Gerlach experiment, but, okay. So it's called the Stern-Gerlach experiment. And the setup is we have a little oven here that's going to be making silver atoms. So you're sort of releasing silver atoms. So you get this little beam. Of silver atoms. Okay, and we're going to have the z direction be up and down like this. All right. Z direction. And they're going to go into a region in which there's this non-uniform magnetic field, okay? So the kind of looks, and I'm just absolutely terrible at drawing this, but, and I probably should have just gotten something from the internet to show you, but I didn't. So maybe I'll do that real quick. Just that I'm such a terrible drawer, it's not gonna really help you too much because I can't draw. Okay, let's see. Give me a sec to find it. Gonna find a good one. Okay, maybe this one. All right. So I'll cover my terrible drawing and make it a little bigger. Okay, so the idea is that you have some silver atoms, and you expect that if you put it through a non-uniform field, that you're going to get, in general, the classical prediction is that, because they have, no interaction really with a magnetic, they're not supposed to have any interaction with a magnetic field. They're just like, silver atoms, right? That you should get just this blue kind of, they're just going to go everywhere, right? They're just, they're going to interact with this magnetic field or not, and they're going to go everywhere. So you're going to get like, imagine this is a screen, and they're going to hit the screen, and they're going to hit it pretty much everywhere. Okay. But that's not what was found. What was found is that you get two peaks. Okay. So these atoms were basically getting separated into what people now call spin up, which are represented by those little arrows going up, and spin down. And the idea is that there is, there's some magnetic moment here of these atoms. And the reason they were using silver is that silver has, like 47 protons, right? So silver, 47 protons, and it has 46 inner electrons, and 1 outer electron. And this 1 outer electron was what's causing this, right? It's causing the entire atom to either be in this pile or in this pile, okay? And because it's a magnetic field that's causing this split, right? People think of this as, well, people thought of it and still do think of it as a magnetic moment, like we've seen before. So for instance, the energy, so if we look at a magnetic moment, or magnetic dipole, right? So let's say we have a magnetic dipole. Then the energy of the magnetic dipole is, the magnetic moment minus mu dot B, right? And so when you think about what is the force in the z direction, right? So a force of deflection on these things, that force, so force of deflection, force causing deflection, right? It would be the force in the z direction, right? Because that's the deflection direction. It's getting deflected up or down on the z axis. Is of course minus the gradient of that potential energy, or that, the energy of the dipole moment. And so it's equal, this is equal to mu times the change in the magnetic field in the z direction. Okay, so we expect deflection if there is a non-zero magnetic moment. That's this here, right? And people were a little confused by this because they knew it had to be due to this one electron. And it was a little confusing where it was coming from. And it turns out it's an intrinsic quality of every particle has this particular quality. It's an intrinsic angular momentum. And people, unfortunately, decided to call it spin. It's not really, nothing is spinning, but but it behaves mathematically kind of like the magnetic, an angular momentum you might get from if you had a particle spinning like a top, right? Mathematically behaves sort of like that, or well, conceptually behaves something like that, right? So people started calling it spin, and the reason really is just from classical physics. So let's think about, in classical physics, if you have an object, you have rotation of that object around. You have two types of rotation. So in classical physics, let's go to our blue color here. So in classical physics, so this is why they started calling it spin, but it is kind of a misnomer. All right. In classical physics, if you have a rotating object, right, something that has any kind of rotation to it, you have two types of rotation. You have one, which is the rotation of the center of mass, right? So if you had some extended object, I don't know, like a little wrench or something here. Can't draw, my pen's going nuts, I can't draw a wrench. But you might have this rotating around a center here, right? So it's rotating around the center like this, but it also could be rotating around its center of mass. Rotation around center of mass. So so this is rotation, this is number one, rotation, but you might also, it'd also be sort of spinning around its center of mass right here, right? This would be two. So there's two types of rotation, or you can break any kind of rotational motion into these two types, right? And so this is why it started being called spin, because we already know about, orbital angular momentum. That's what it's called, the L, right? That's kind of like rotation of the center of mass, right? And so in classical physics, we would call that orbital angular momentum because it's orbiting the center, right? Orbital angular momentum is 1. Quote, in quotes. And this is also, when we think about the hydrogen atom, right? This is the angular momentum that we've already looked at, right? The L, right? This is the angular momentum of the electron spinning around the atom, right? Moving around the atom. R, right? R cross P. That was our L, right? So this is the L that we've been talking about. This here, right, in classical physics, right, would be a spin, right? Okay, and now this is where we're going to call it. I'm going to call it spin here. I'm going to put spin here. But this is where the breakdown between classical physics and quantum mechanics comes in, because yes, in classical physics we would say, yeah, it's spinning around its center of mass, right, and it's going around the center, whatever the center of rotation is, right? But in quantum mechanics, while this, yes, is really R cross P, right, due to the momentum of the electron, it has quantum mechanical properties like we saw, right? You could only know L squared and one of the components, right? You can't know all three like in classical physics. This here, the spin around the center of mass is not, the electron is not really spinning around its center of mass. That is not happening. In fact, if you were to calculate what would happen if the electron was really spinning around its center of mass at the level that it would need for its intrinsic, right, angular momentum, it would fly apart. It would have to, spin at many times the speed of light. Okay, so it is not the electron spinning around its center of mass, and so the reason that would even give you a magnetic moment, right, is that the electron's charged, and if it's spinning, you would get magnetic field, like a magnetic moment that could interact with magnetic fields. That's right, but it's not really spinning. It's just an intrinsic property of that point particle, and the electron really is a point particle. Okay, yeah. So it'd be it's not that. It's kind of an unfortunate misnomer. And but it is interesting that it behaves like a magnetic moment, right? It behaves like something you might get from a spinning top with charge, right? So it's really it's a very, very interesting quantity, but it is not spinning around. It's just an intrinsic quantity, and all particles have spin, and we're going to talk about all the different kinds of spin. But first, just in quantum mechanics, right, the algebra of spin is very much like the algebra of the orbital angular momentum. Okay, so in QM physics, the spin algebra is very similar. So for instance, S I should have said we're going to be calling this S. Okay, spin. Like I said, misnomer, but we can't do anything about it. Right? That's just the way we got to call it spin. Okay, so SI, the commutator of these two. So for instance, with I could be, I equal X, Y, Z. Okay, is just like L, and I'm going to write it in our sort of fancy way, Leibniz Vita I, J, K, S, K, right? We never wrote the L commutators this way, but we could have, right? So for instance, this gives you S, X, S, Y is I, H bar, Leibniz Vita X, Y, Z, which is just S, which is just one, so you get SZ, right, etc. Yeah, equal 1, 2, 3, right? Okay, so that algebra is the same, and very similarly, you can't have simultaneous eigenfunctions and eigenfunctions of, say, Sx and Sy, just like you can't have simultaneous eigenfunctions of Lx and Ly, right? Same exact thing, but you can have simultaneous eigenfunctions of S squared, right? The square of the total angular momentum, and Sz or S or X or Sy. Traditionally, you do simultaneous eigenfunctions of S squared and Sz. Question?
What about for like inverse commutators like Sy, Sx? Would that still be I, H bar, Sc?
Remember, Sy, Sx is just going to be the negative.
Okay, so
of SS, Sx, Sy.
but like so Sy, Sz would be I H bar S I?
No, so S Y S X, let's say.
No, S Y S Z.
S Y S Z. Okay.
I'm sorry. I understand that it's just the inverse, but what about like the other ones in the you just
Okay, let's see. So Y is 2 and Z is 3, right? So
okay.
we have I H bar Levi Chavita. Um, uh, so the I is the 2, the J is 3, and K can only be 1, right?
All right.
And so this is going to be 1. And 2, 3, 1, right, is a cyclic permutation. So that's going to be I H bar S1. Yeah? Remember how the Levi-Civita tensor works, right? If you switch any two of the indices, so you start with 1, 2, 3, you switch any two of the indices, you get a negative 1. But if you can cyclically permute, so like 1, 2, 3, and then you're putting the 1 in the back, 2, 3, 1, and then 3, 1, 2, those are cyclic permutations. Those all stay positive 1. Yeah? Okay. So remember, we can have, just like with L, we can have so we can have simultaneous eigenfunctions of L squared and, of S squared and any of the components. Again, it's traditional to take S squared and SC. Okay. So we can write, and in fact, I'm not going to go through all the algebra to find these, but we can, I'll just write it down. So let me first tell you what a particular spin state would look like. Just like with L, remember with L, we had the quantum numbers L and M, right? Just like with L, the S has quantum numbers S, little s, and M sub s, okay? So when we write, so there's a way of writing a particular state. Of course, you could write YLM, right? Because we know that the eigenfunctions of the L squared and LZ operator are the circular harmonics. But people often write it like this. They'll write a ket, and they'll say it's a LM. And this is really a shorthand for the eigenfunctions of both L squared and LZ, right? So this ket here is short for eigenfunctions, this guy. Short for eigenfunction of L squared and LZ. Very messy, I'm sorry about that. Okay? So similarly here, here we don't need this. So similarly here, we're gonna write, and it's up here, but I'm not gonna write it down there. So we have S, M, S, it's a little s, by the way. So it's supposed to be a small s, not a big S, not a capital S. And this is short for of S squared and SZ. Okay, this intrinsic angular momentum of the electron. And so when I write down the eigenvalue, eigenvector equations, I can write them in terms of this ket. Okay, so S squared acting on the ket, little s, ms, is H bar S plus 1, S, ms. Let me check something here. H bar squared, yeah, H bar squared. Sorry, typo. Okay, and which looks a lot like the L squared equation, right? because remember, if the L squared, let's see, so we had L squared acting on LM was H bar squared L plus 1, right? And then the state, right, that we're using here, this guy. Okay, and then our for the SZ acting on that state, right, the eigenfunction, the simultaneous eigenfunction, is just like the L1, it's H bar MS, SMS, right? Okay, so they're just like we had over here. LZ on LM is H bar M LM. Again, remember the LM is just a stand-in for my spherical harmonics, right? It's just a ket version of spherical harmonics. Okay. All right. Okay. So and M, right? So the difference here is that little s. So remember, L was just integer values, but little s can take on values like this: 0, 1/2, 1, 3/2, etc. So up by factors of 1/2. Okay, and M, just like with L, right? Little ms, just like the M over here, right? So let's just keep track of both of them here. So L can be 0, 1, 2, 3, ... And remember that M can go from minus L to 0 to L in integer steps, right? Okay. So MS, very similarly here, can go from minus S, oops, wrong color, sorry, minus S, minus S plus 1, right, ... to S minus 1, so 0, sorry, S minus 1, S, right? So that similar thing as we have over here. I didn't write it all out, but right, very similar. So the algebra is very, very similar. And in fact, remember that we had our L plus minus operators, our ladder operators. So we had L plus minus operators, which were LX plus minus I Ly. We have similar operators here. We have S plus, dang it, wrong color again. We have S plus minus equal the X component of X plus minus I times the Y component of S, right? So just like in the L case. So the algebra is very, very similar. Okay. Okay, now here's the difference. Here's one of the differences, and that is that every elementary particle, okay, has a specific and unchangeable value of little s. Okay, so for instance, I see you're still writing, so let me just break for a second. Tell me when you're ready. Are we good? New layer? Oh, I gotta get rid of that. Give me a second. Okay, Okay, why is that still visible? Oh, okay, I got it. Never mind. Give me a second here. Sorry, I didn't label this right. Give me a second to label it, otherwise I'm gonna lose my organization thing here, which is not the best, but. And then here. Okay, all right. So, like I said, so you're kind of used to, let me back up a little bit. So think about the case for L, for the orbital angular momentum, right? The R cross P. Remember that we had different values of L, right? Little L. So we had different values of little L. So for orbital angular momentum, we had different values of little L. Right? So you might have let's say for the hydrogen atom, right? You might have, 4 different states with L equal 1, right? Or sorry, you would have 4 different states with a particular energy with different L's. That's what I meant to say, right? Remember that? We went through that a few times. So different values of L for the same electron, meaning it can be in many states, same atom. That's not the case with the spin angular momentum. So for spin, every particle, every elementary particle has one value of S, little s, that cannot change. It is an intrinsic property of that particular particle. Okay, so for instance, electrons protons, neutrons, all have S equal 1/2. We say they're spin 1/2 particles. In fact, we're really only going to deal with spin 1/2 particles in this class. But just to point out, photons, they have S equal 1. Okay. There's weird ones like, the graviton, right? The mediator of the gravitational force has spin equal to 2. Weird things like a delta particle has S equal to 3/2. Okay. You cannot change the graviton spin, right? The graviton has spin S equal 2. Electron has spin S equal 1/2, and that's that. You cannot change it. It's like I said, intrinsic to the particle. Now, because atoms are made up of these particles, right? They can have their own spin. So, for instance, your say helium-4. Okay, this has spin 0. Okay. And helium-3 has spin 0.5. You can probably guess why. Right? Right. We have a class of particles which are called fermions. You might have heard of that, fermion. They have half integer spin. Say, have half integer Okay, so which of the ones up here in this list were our fermions?
Electrons, protons, and neutrons.
And?
Delta particles.
Delta particle, that's right. And then bosons, and I know you've heard these terms, have integer spin. And they behave very, very differently, these things. You've probably heard about like a Bose-Einstein condensate. Those are the properties of things like that, and the properties of, say, superfluidity really depend on this spin. Okay, and in fact, all of the chemical properties that we know and love are really due to spin, right? So if you think about the Pauli exclusion principle, you've probably heard about in chemistry, right, where the two electrons don't like to be in the same state. They're referring to spin. If you have one spin up electron in an orbital, the other one has to be spin down. Okay, and this accounts for so much of the chemical, pretty much all of the chemical properties of the elements, as you know from chemistry, right? So very, very, very important. Now, so the electrons don't like to be in the same state because they're fermions. So it's really fermions that have this issue. Bosons don't really mind if they're in the same state. Okay, so that causes a lot of really interesting properties. Okay. And here, for the rest of the class, we're really going to concentrate on spin 1/2 particles, because that's the most relevant for, say, the hydrogen atom or any atom, right? We're not talking about the spin of the atom now. We're talking about the spin of just one particle, like the electron. Okay, so we're going to concentrate on spin 1/2, and so concentrate. Because we like electrons. Okay, so that's little s equal 1/2. And remember, that does not change, right? So once we say this is what we're dealing with, little s does not change. So this means, all right, so let me go back and write down some of the properties of our S and M and MS, right? So remember, if we have S that's some value, MS can go from minus S plus 1 ... 0, minus, or sorry, S minus 1 blah 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 S, right? So if little s is 1/2, what are the values that are possible for little ms? Okay, so this is a this and a this. What does that mean, though?
Plus or minus 1/2.
Numerically, what is it?
Plus minus 1/2 and 0.
Good. Yeah. So 1/2, and it's not 0 though, right? Because you start with minus 1/2, and when you add 0, what do you get? Oh no, sorry. When you add 1, what do you get?
Just 1/2.
Plus 1/2, right? So you can't have 0, right?
Oh,
so
okay.
Minus 1/2 and 1/2. Yeah, you could certainly get 0 if s is 1, right? But for instance, photon. but not for the electron. Okay, so that means there's just two eigenstates, right? There's two states that are eigenfunctions. There's two of our kets, right? So we have our ket. Remember, our ket is SMS, and we have one that looks like this. So we have 1/2 minus 1/2, and we have 1/2 plus 1/2, and these are referred to as, spin up and spin down. Yeah. So visually, again, it does.
Is there a reason why spin up is the negative one? Or is it just
Jesus.
semantics?
Me writing the wrong thing, that's why. Yeah.
Huh.
Nope. I don't know why I did that. Okay, down and up. Okay, that makes more sense. So, so think about it, right? We know that this is not really, a top spinning or something, but certainly has a vector nature to it, right? So think about the spin down. It's like it's all the z component is taking up all the angular momentum, right? All 1/2, roughly, and it's pointing down, right, along the z-axis, and the spin up is pointing up along the z-axis. Yeah. All right. Something like that. All right. So the general state of a spin 1/2 particle is going to be a linear combination of these two things. And by the way, people write this spin down with a little arrow like this in a ket, and this spin up with a little arrow pointing up in a ket. Okay, very common notation. The general state of this spin 1/2 is going to be some linear combination of these two states, right? It's usually called a spinor, right? So a spinor, so the general state is a linear combination of up and down, and it's called a spinor. Okay, and usually written like this chi. I know I'm bad at writing chi, and would look like this, where we have a matrix representation, right? Two-dimensional matrix, vector, right? Column vector, which is the representation, which can be written as A times chi plus. This is the shorthand for the, up, and then plus B times chi minus. This will be down. And then in sort of the vector notation, right? In column vector notation, this is a 1, 0. And this is a 0, 1. Okay, just different ways of writing this. This is kind of the linear algebra version of writing a linear combination. And again, it's a two-dimensional space, right? Because we only have two possibilities: spin up, spin down. Okay, and if we look at s squared, acting on our chi plus, right? So acting on the up state, where remember that's h bar squared s plus 1. Remember, s never changes. It's 1/2 times chi plus. And so this is going to be h bar squared times 1/2 times 1/2 plus 1 chi plus. And that's going to be h bar squared This is 3/2, so it's going to be 3/4 chi plus. And this eigenvalue never changes. This is what it is, right, for s squared, because it only depends on s. Okay? Again, I can write this a whole different way, right? I could say this, I could write this as s squared on the up is equal to 3/4, oops, sorry, h bar squared up, right? Same thing. Okay. But that eigenvalue does not change. Now, remember when we were back in chapter 3, we said that all operators can be written in matrix form, right? And we didn't do a whole lot with that, but we did do a couple of problems with that. So we're going to do the same thing here. Because this is a two-dimensional space, people usually are pretty much always working in, at least for electrons, in kind of matrix notation using linear algebra. Okay. All right. So let's look at how do we get the matrix elements. So we want to make s squared into a matrix form, right? Into its matrix form. So remember, let's go to pink color here. Let's get matrix form of s squared. So the matrix form of the plus here was this 1, 0, and the matrix form of the down was this 0, 1, right? So now we're after the matrix form for s squared. And if you remember from chapter 3, how to get matrix elements of your operator, you're basically writing your operator in the basis of these, of the plus, of the up and the down, right? So you're using your up and down cats as your basis to express your operator in a matrix form. So if you recall, if we want, let's just write down the general form of s squared in matrix form. What would it look like? Well, it's going to be a 2x2 matrix, right? It's going to be s11, s12, s21, s22, right? Those are just the indices, okay? And the one state, might as well call it the up state, right? Right, so we might as well let that be the up state. So if we want s11, remember we have to do this, which is up, right? So that's 1, and s squared, and then acting on 1. Remember this, I hope, from chapter 3. Okay. And so here, that's pretty easy because s squared acting on the up, right? Oh, and I forgot to mention here, actually, let's back up a tiny bit. Let's go back up here, because I just told you what s squared on the up vector, right here is. This is just different notation, right? What is s squared on the down? What is that? I mean, it might be helpful if I write down the general equations again. So the general equation.
-1/4. H bar squared -1/4 chi.
Hold on.
Negative.
So let me write down the equations. Right? These are the eigenfunctions that are simultaneous for s squared and se. Okay? So what is it? That was an incorrect, Jackson. Remember, the down is short for this, right? Which is in this format.
Would it be the same?
Yeah.
This
Yeah, absolutely, right? Remember, S, little s. Once we've said, hey, we're dealing with particles that are spin 1/2, it never changes, ever. And s squared, the eigenvalue of s squared only depends on little s, not on m, or m sub s, sorry, right? Little s. Okay, so that's true. Okay, so let's keep going with our pink calculation here. So s squared acting on the up gives me h bar squared 3/4 up, right? So we get this 3/4 h bar squared up. And of course I can bring the 3/4 h bar squared out, 3/4 h bar squared, and then it's going to be up, right? Up, inner product with up, which is 1, right? Remember these are normalized, although we haven't said anything about them, but they are. And you can look here in this matrix form here with the 1 and 0 and the 0, 1, they indeed are normalized, right? So let's just take a look at that as an aside in this format here, right? The up inner product with up is a column, a row vector 1, 0 dotted with a column vector 1, 0, and row times column gives you 1. Okay. Similar thing's going to happen with the down, and you're going to have column vector 0, 1. Row vector 0, 1 with 0, 1 column vector, which gives you 1. What happens when I do this? Up inner product with down.
so it's just an identity matrix.
What is?
Or the s squared, it would just be well, not an identity, it would be 3/4 h bar squared along the diagonal,
Absolutely. Yeah,
and
absolutely.
everything else would be 0.
Right. But look at this here, just to point out again, right? These are orthogonal states, because if I say the up, remember, is 1, 0 in a row vector in this, right? And then this is 0, 1. This, row times column gives you 0. Similar thing here with the down first and the up next. These are orthogonal states. And as Jackson said, that has consequences here in this calculation, because this is going to be 1 here. And anytime we have, a matrix element that's off the diagonal, it's going to give us 0. So let's just write it down real quick. S12 is going to be up, and then s squared acting on down. And that's going to be 3/4 h bar squared. And then this inner product of up with down, which of course is going to give us 0. So this element is 0. Similar with S21, so I won't bore you with that. S21 equals 0. And S22 is down, S squared down, which is 3/4 h bar squared down, which is 1. All right, this is 1. And so it's just 3/4 h bar squared. Okay. So this matrix now is 3/4 h bar squared times the identity matrix 1, 0, 0, 1. Yeah, just like Jackson said. Very good. Okay. And let's go on and see about SZ. Okay, I need to get a new layer though. So let me know when I can. Okay, power's good. Yeah? Okay. I will get a new layer and label it while you guys finish up. Oops, I think there's two of them named 2. Haha. Okay. Hold on a second, let me fix that because it's going to make me look crazy. So this is going to be, this is 3. And this here is going to be 4. Okay. All right. So again, let's write out the equations that we have for the eigenfunctions. We have s squared on SMS. I'm just rewriting things so we have it sitting here. H bar squared s plus 1 SMS. Now this works for any spin, but we're doing spin 1/2. SZ on SMS is H bar MS on SMS. And I didn't write this down, but this is what happens with the ladder operators. So the ladder operators S plus minus acting on SMS. We didn't write it down. Sorry. Is H bar, and then this big messy thing, SS plus 1, and then minus MS plus minus 1. Okay, and then it raises your Z component by, raises or lowers, sorry, your Z component by 1. Okay, remember these are raising operators. They don't leave the state alone. These are not eigenfunction these are not eigenvalue equations here. Okay, just writing that down because, you know, we're going to need it. We don't have much time left, but okay. So let's look at the matrix elements of, matrix elements of SZ. Okay, all right. So again, SZ matrix elements are going to be, you know, SZ11, SZ12, SZ21, SZ22. And so SZ11 is going to be just up, SZ up. And we haven't actually written down for our spin 1/2 particles what this would be. So let's do that. And I'm going to ask you guys to tell me what they are. So what is SZ acting on our 1/2? This is our up ket. Well, here, let me, sorry, one more. I'm going to write the up and then I'll write what it is. So remember the up ket, spin up ket is, looks like this, SZ, it's the little s equal 1/2 and MS equal 1/2. So what is that? What happens, SZ acting on that, what do I get?
It would be H bar 1/2.
H bar over 2, good, times the up ket again, right?
Yep.
Good. What about SZ on the down ket?
Negative H bar.
Negative H bar over 2. Down ket. Good. All right, great. So now we know what this is, right? So this here in our green is going to be H bar over 2, and just H bar over 2 because then we're going to have up inner product with up with just 1. And then SZ12 is going to be up SC down, which is going to be negative H bar over 2, except now, of course, we have an up inner product with a down, and that's going to be 0. Okay. Similarly, SZ21 is 0. And SZ22 is down SZ down, which is negative H bar over 2, and then times 1, because down, inner product with down is 1. And so SZ in matrix form, is H bar over 2, 1, 0, 0, minus 1. Yeah? Okay. Okay, let's see what happens when we apply our ladder operators, okay? So we now know what happens when you apply S squared to the up and down kets. You get 3/4 H bar squared. And those are, remember that the kets are eigenfunctions of S squared, so you get back the ket. And we know what happens when we act SZ on the up and down kets. Okay, let's see what happens when we act the ladder operators on the up and down kets. Okay. So first of all, let's look at S plus on up. What do you think that is?
It'd be 0.
Yeah. Why, Jackson?
Well, in that case, it would be S plus 1 minus MS times MS plus 1 would equal each other out. So you just get the square root of 0, and which is 0.
And the other reason is, look what it does. It raises MS by 1. You can't. MS is already at its highest possible level. It's 1/2, right? MS is already 1/2. You can't raise it by 1, right? That would make it 3/2. So that's another reason, right? That's why that works out that way, yeah? Okay. What about S plus on the down ket? What happens there? Did we do it real quick before we end the class? So it's H bar. So we have 3/4. We know this is going to be 3/4, right? This thing. And then minus 1/2. And then it's plus, right? So it's exactly the same thing. So wait a second. Oh no, it's minus 1/2. So
Also 0.
No, plus 3/4, right? Because this is, oh, and it's not plus 3/4. I'm doing the math wrong, but let's do it a little carefully. Okay, so minus, and then a minus 1/2. So that's plus 1/2. Then we have a minus 1/2 plus 1. So that's positive 1/2, right? And then we have this is going to make this the up ket, right? Because it changes MS by 1. Goes from minus 1/2 to 1/2, right? Here. Okay. And so what do we get for the coefficient? We have H bar. We have 3/4. We have plus, so this is going to be 1/2, so plus 1/4, right? So you just get H bar. Oops, and I left off my ket. Sorry about that. And this is going to go to the up ket. And that's just going to be H bar times the up ket. Yeah? Notice how S plus changes it from down to up. Right? It's supposed to do that. It's ladder operator. Okay. All right, that's it, guys. Remember about test corrections. Remember about, I hope you turned in the homework that was due today. Remember that you have the quiz problem due Thursday night, right? Okay. All right, guys. See you later. And Haley, you're hanging on for a second. Okay. What's up? I can't hear you.
Do you mind turning off the recording, please?
Oh, yeah, duh. Sorry about that.
No worries.